Cool. So hi everyone, my name is Andrew. I'm a postdoc at the Computational Media Innovation Centre, or CMIC for short, at Victoria University of Wellington. Today I'll be continuing TJ's talk from Tuesday about photorealistic XR. So on Tuesday, TJ talked about the digital media ecosystem, some concepts behind lighting, and which was used for MR360, and our most recent work used for telepresence and telecollaboration using our platform called AVT. Today's talk will be going also on the topic of lighting, but in a different direction. We'll be looking at our intelligent media processing program, which is set up to solve problems in XR using AI. We'll cover photorealistic mixed reality rendering, which will motivate our main two topics called the illumination space, as well as inverse lighting for mixed reality. And then we'll conclude with some other sort of areas in which we use AI to solve some XR problems. And I also have a demo as well, a live demo. We'll see how that goes. So as TJ mentioned in his talk, we have three groups with different expertise. They're called CMS, UXR, and AMP. The content of this talk is in the CMS area. We'll be looking at using technical solutions to solve XR-related problems. So the outcomes of this work will be a technical solution that innovates the digital media ecosystem, but this leads to new research opportunities and collaborations or prototypes that we can develop with the other groups. And we can also talk about some of these outcomes at the end of this talk as well. TJ also touched upon some of the programs we have at CMIC, and explicitly the content of this talk is AI and using AI to solve these XR problems, which is intelligent media processing, the third program, it covers AI, big data, machine learning, using deep neural networks to solve these problems. And I'll be going to a couple topics in particular. So the focus of this talk is about lighting and to solve the problem of seamlessly blending digital content into the real world. So we can see here in a typical AR sort of app like Pokemon Go, you have Pikachu that's just overlaid. Whereas if you want something more like where it looks like it actually belongs in that world, where it seamlessly blends into that world, you need a more intelligent solution, such as the concept image on the right. And on the figure on the right is about collaboration, where you can have remote communication like we are doing right now with Zoom. But if we're able to use AI to figure out other properties in which we can better immerse ourselves into remote communication, we can also try to solve this problem as well. So in TJ's talk, he was talking about using 360-degree panoramas that they could use in what's called image-based lighting, or IBL for short. So this is a technique where they use high dynamic range panoramic images that capture the surrounding environment. So it's a photo that looks in every single direction around you. And then that way we've got every source of light coming in from every direction, so we know the complete lighting information from this photograph. And so this is typical in VFX, in the film industry, and in games also start using IBL as well. So here's an example you can imagine where we've got a photo and we're taking a photo of a scene, and we've got our background photograph. And if we have a 360-degree camera located in that same room, we can capture that. And then we've got complete scene lighting information. And then we can light virtual objects which look like they are illuminated the same way as those real objects in that room. So that's a seamless composition, we'd call that. In our talk, we're going to be looking at the problem where if the 360 camera wasn't available. So if this was not there, how could we achieve high quality, high fidelity lighting? And so this leads to the technical challenge of our talk. Which is about inverse lighting. So typically in a normal rendering setup, like a forward rendering, you would have on the left here your scene file that might be like in Maya or Blender or something. You've got your 3D geometry, your lighting, camera, materials, everything set up. And you go and hit the render button, and you've got some other effects set up in a person's then that you composite into your rendered scene, and that will produce this image. In our case, we've given a partial view image, and we're not given the full 360-degree environmental information. So it's like we've got that right image, and we don't have that scene information on the left. That's not given at all. All we have is that photograph. And so if we wanted to blend a new object into that photograph, we need to recover that scene information, and that's called inverse rendering. And so we're going to look at an RGB image and then try to just figure out, okay, what would the lighting look like? Inverse rendering covers other areas, like if you want to estimate the camera properties, like the angle that your phone is looking at the floor or something, without assuming you didn't have a gyroscope or accelerometer, that would be like, if you tried to figure it out, that would be inverse rendering as well. And so in our case, so as another example is, if you have a photograph and you're going to try to put a virtual object into that photograph, and let's say that photograph had some depth of field. Ideally, the virtual object that you have when you put it into that photograph has that same depth of field effect as the rest of the photograph. And so to do that, you would need to know the focal length of your camera as well as the depth of the image. And so you would have to do some inverse rendering to figure out those properties. So then you could then re-render the virtual object with the same properties as the rest of the photograph. In our case, so we're given a photograph, we're given some geometry, and we want to estimate the real world lighting. And if we can estimate that, you can see that bunny and dragon there, rather than being naively rendered, it would be nicely illuminated such that it matches that background photograph. So that's the setup of the two solutions that we're going to be looking at. So the first is called illumination space. So it's looking at big data and processing big data and extracting features from it and whatnot, with the main target of art direction. So the idea where you have an artist has a photograph and they want a tool to assist them in terms of looking through a database of these 360-degree light sources, so they can then do manual composition and tuning as an artist would. The other one that we're looking at is specifically inverse lighting, in which you're given a photograph and we're just going to use a machine learning algorithm to then estimate from that photograph what the lighting conditions are that would be suitable for that photograph. And that's instead of art directed, that's fully automatic pipeline, so it might be suitable for like an AR application. In both scenarios, they use a HDR environment. So the HDR environment maps, they both use databases. It's just the application area is a little bit different. One's art directed and one's fully automatic. So we'll begin with illumination space. So the problem is that we've got a large data, typical in VFX studios, they'll have a large database of these 360-degree panoramas that they've captured. When they go out and set to film, they often will capture a panorama and they'll add that to their database. And often these artists will collect, they'll collect a huge number of these what I call radiance maps or environment maps. And then they would like to reuse that data internally when they go, pre-visualize assets. They like to look through their lighting conditions that they've captured and evaluate the assets, which is called look development. So they need a way of managing that database. And so in this research, we looked at ways of extracting features, like looking at the entire database of these light sources and extracting information about them to semantically organize them so an artist could then intuitively browse through that database. So here on the left here, we've got some photograph that an artist would like to composite into, but they need to know some nice lighting for that target image, and they'll have to navigate through this database to then select some light to apply to this scene when they composite a virtual object into it. Just as an overview of this process, so it's first there's a light feature definition and extraction stage, where we're given like this database of unorganized radiance maps. So again, the radiance maps is what I refer to as these 360 panoramas, in which they contain radiant information per pixel radiance. We then, given an example from that database, we're going to detect some high frequency information, so the dominant, most prominent light sources, and we're going to parameterize those dominant light sources into a few features, and then we're also going to encode the general ambient tone of that radiance map as well into a few features. So we end up converting a panorama, which typically will have millions of pixels within it, into a small set. In this case, it shows about 9, but I've actually reduced this to 5 now, 5 features. So the artist will have a handle of 5 features, which they'll navigate that database for. So then from those features, we can visualize them in scatter plots, and where every point here corresponds to one of those 360 images. And so they could, go through and browse this database, which is now organized according to some parameters. So then they could, input, for example, their mouse position, and then it will give back an example. So the first step in this procedure is detecting the lights. So we can see we need to detect these lights to then reparameterize. So there's going to be a few stages. One is detecting the lights, parameterizing those lights, and then also summarizing the tone of the radiance map. So for the light detection stage, the idea is that it needs to be automatic. We don't want an artist to manually annotate the entire database. And also, since we're trying to reduce all of these pixels into as few parameters as possible, we want to detect only the most important lights. We don't want to parameterize too many. We want to focus on the important ones. And the way we did this is looked at it in terms of shadows. So, because if you look at this as like a normal texture image, there's a lot of high detail information, and there's too much to parameterize. And you could imagine that this map to a spherical ball, in which it's like a chrome ball that's a mirror. But if you convolve that to, say, a diffuse ball, there's much less information there, and if you, it'll be easier to parameterize when you start blurring out the information. However, choosing how much to blur, it's too many sort of parameters to handle. And also, when you look at blurring them, you're also view dependent, because it's a specular component when you're going through the different blurry levels. So we looked at focusing on the shadow, which is not view dependent, and it also doesn't remove too much information like a diffuse sphere would. So here on the left here is, you're looking down on a plane in which there's like a cup or a cylinder, and it's casting shadows in all directions around it. So you can look at it like a sundial. In the middle is its shadow profile, so we're just highlighting where the shadows are by doing a difference image. And on the far right is where we're using the just noticeable difference. So we're looking at what can you perceive as a shadow. So even though this could be considered a shadow out here, you can't actually see it very clearly over here, even though technically there is a little shadow out here. We're going to threshold that out. So all of this stuff, information, is not considered a perceptible shadow. And then using this, we're going to have an algorithm that detects lights that only cast perceptible shadows. So we're going to go from this image down to the mask. And so the algorithm is as follows. We have our panorama, we convert it. We're going to look at the upper hemisphere only and convert it to superpixels. So rather than looking at every pixel, we're going to look at patches. And then this is our low resolution shadow profile, which I showed you before. So this contains only shadows that we can see, because we thresholded out the other shadows as well. And so we're going to go ahead and start doing what we call a matching pursuit algorithm, which it's a greedy algorithm where we go through every superpixel and select only ones that contribute to casting that shadow image, casting a shadow within that shadow image. So we organize them from most brightest to least in terms of the superpixels, the most brightest superpixel to the least. And we go through and see, does it contribute to the shadow? So here, that's that first pixel selected, and that's the shadow it's casted. And that's within sort of this perceptible shadow image. So we're going to keep it. And we're going to keep doing that for all superpixels until one doesn't really contribute. And so in this case, this one doesn't really add any perceptible shadow. It might be casting a shadow in a direction where there's no what we consider a perceptible shadow. And so that way we ignore that superpixel and keep going until we have our final mask. And so this light detection algorithm is designed to be automatic. So rather than having like a thresholding algorithm, where you have to choose a threshold, this happens automatically. And it's designed to be for panoramas because it's considering how light in the panorama impacts one another. So if you have a bright light here, but a very bright light on the other side, that very bright light is going to dominate the other one, and it will only select the very bright light. And so for each of these bright lights, we're going to reparameterize them now. And so we have a parametric model. In this case, it's got a spherical Gaussian, which we fit to these lights, and it's actually anisotropic. So we've fit the exact shape of this, and we do that for each light. And then we have a process in which we look at those models and summarize them into as very few features, specifically the most prominent. The sigma is the area, like the softness that light, well, the area of that light, and in terms of shadows, it's how soft that light, the shadow is from that light, the elevation of that light, as well as what we call complexity. Because so these first two are going to look at the dominant light, the most salient light, and say how big is that light, what is the elevation of that light, and then the FC is complexity, where it looks at all of the lights together and summarizes how complex the lighting conditions are, and it looks at kind of the spread of the lights around the panorama. And then for the so that summarizes the bright lights of the panorama, but we also want to summarize the general tone that this panorama has in rendering. And so the way we do this is that we take the panorama, and typically when you can see an example here of a sphere rendered on a plane. If we want the general tone, you would look at a diffuse sphere, but even on a diffuse sphere, there's a lot of different colors and whatnot here. So we wanted something grounded in which an artist would have a one-to-one correspondence between the panorama, the color that the colors that we've selected as the features for the radiance map, and what those features would map to in the rendered scene. And we decided to go for a diffuse plate. So this is just a plate in which it's parallel with the floor, and so it represents the total energy coming in from the upper hemisphere onto that point. And we're looking at the hue and saturation of that now. So we take the hue and saturation of basically the up direction of this, the diffuse up direction, and that summarizes the 5 features. So we've got the 3 high frequency features, as well as the 2 ambient tone features. This is the result. So you can see the features are plotted on the right. So this top right scatter plot is the high frequency feature. So there's 3 dimensions, the X, Y, and the color is the 3rd dimension, where it corresponds to the size and elevation and complexity on the 3rd dimension. And then the other 2 features are its hue and saturation. And so here's an example where for A, we're putting our pointer here. So we're going to go low elevation, very soft, and we're also going to go for blue tones. So we put it here. And so these are low elevation, very sharp, sorry, so the size is small, so the lights are very small, so they're very sharp shadows. So we've got these long sharp shadows, and these are the points that live in this space. If we drag A to B, then it's becoming softer. So we can see that the tone is very similar between the two because we kept B at the same location in terms of tone, but the shadow has gotten very soft. For C, we've gone up. We've raised the elevation of the light. And so we can see the shadows have gotten shorter. They're still very sharp, and we've also dropped the saturation down, so there's a very quite white, desaturated lighting. And then for D, we've raised the sharpness, so they're fairly short shadows, sharp shadows, and there's multiple of them. I was hoping to do a live demo now, so I'm not sure how this will go. It'd be good if Holger or something can give me feedback on whether or not he can see this. So I'm just going to back out and switch to my code here. Can you see this, Holger?
Oh yeah, we see your. I don't know what we should see, but we see now your PowerPoint, editor view.
Okay. So okay, I've got my demo up now. Can you see that? Probably not, right?
No, so okay. Probably on a different screen.
Yeah.
Yeah. So probably you share your desktop, probably.
Yeah. Cool. So you can see that?
Yeah, much better.
Great. So this is the actual interface. If I turn off the ambient features, so you can just see here the high frequency features. So if I raise this, you can see that shadow getting shorter. And if I pull out to the right here, you're going to see this very overcast lighting where it's the light is overhead but very soft. And as I pull it down, the light is more towards the horizon, so you get a slight spill of shadow to the left, but it's still very soft as well. And you can see that all of these examples are similar because they all live within a similar space here. So if I go back to the overhead lighting, you can see it's all sort of soft overcast lighting up overhead. Going back to the sharpness, so these are the sharp shadows. So you can see they're all quite similar. And so an artist can kind of go through and be like, okay, I like something, and then they can select it. And on the top right there is a little preview renderer of that IBL. If I reintroduce the ambient lighting, so if I turn on ambient lighting and turn off the dominant lighting, so you can see it's focused on tone. So there's your blues going down to your desaturated whites, and then coming back up to your reds here. And an interesting part of the system that we found was if you take a database, it naturally falls on this warm to cool spectrum. You can see that's like basically one dimension right there. And so most natural data will have cool or warm light. Unless you go out of your way, you can get some forest or something, or like, these weird caves. You can try to get data points out here. So I think it's an interesting way of maybe seeing where there's holes in your database. So you can see, okay, you don't really have any data here. Maybe you could go capture more of that, or you don't have any surreal purple lighting, and you can go get some of that. And then if I go back to the dominant lighting, cool. So one thing you'll notice here is that the shape of the shadow is very similar across all of these, but the tone they're all different tone, and that's because I've got the tone turned off. If I turn that on, then it might not be all perfectly the same in terms of the shadow, but you're going to get kind of a weighted combination where it is trying its best to get similar shadows and similar tone as well. You'll notice that alpha in this plot as well changes. So if I move the hue around, you'll see in the top plot, if you look at the high frequency plot above, the alpha is changing. So it tells you where the data points exist. So if I go around here, if I pull to around here, I can see data points exist out here. So it's a way of informing the user that data exists somewhere in two different scatter plots. That way they're not looking somewhere in a sparse area. So if I go here, I'm not going to get, sensible feedback. Cool, I'm going to go back to my slides now. So Holger, can you see my slides okay?
Yep, yeah, illumination code, light demo, yep.
Cool. So that was a demo of a way of processing a large database of these radiance maps using feature detection, and where the application is for an artist to browse that database. The next part is focusing more on inverse lighting in terms of a complete automatic pipeline where you've just given a photograph. We're going to try to automatically learn using that same database. We're going to learn that relationship between what a photograph looks like, the features within a photograph, and automatically infer what the panoramic lighting would be. I'm going to do this using a CNN. So to begin, we're going to look at a standard sort of CNN, and so you don't need to know the details of what's going on here, but the basic idea is that you've got some input photograph coming into that CNN. It's going to be processed, and it's going to spit out a 360 panorama on the outside. So that's your standard network, and we're going to look at improving it in a few ways. So first, I want to show how we're going to use the standard network first. So first, we're going to generate some data, and we're going to look at outdoor and indoor cases separately. This is because their lighting properties are very different. The tone is completely different, as well as the type of lighting, where rather than just having a sun that goes across the sky, you've got lots of different cases for indoor scenes. So they're quite different. So we train them on different networks. We then augment the panoramas. So augmenting is a process of just making the data more suitable, as well as generating lots of data, because a neural network requires lots of training examples. For the outdoor case, we had the 360, some 360 data set, which is actually low dynamic range, so it's not actually suitable for lighting. And we inverse tone mapped it to be HDR. For the indoor case, we did a thing called spatial warping. And the idea is that when you capture a 360 image, that photograph is exactly correct for the point in which the camera is located, but it's not actually correct for any other point nearby for indoor cases, because the lighting is not, there's spatial variation. So if I stand in one position of my room and walk to the other side of my room, the light direction changes. Whereas if I do that outside, the sun is so far away that it's basically parallel, and you don't have to worry about that. And so since we're not, since we're compositing into different parts of this panorama, we need the lighting at those different positions. So for outdoor, we're going to extract a photograph. For indoor, we're going to extract a photograph. And now we've got, for the neural network, it needs an input and output pair. So the input being the photograph, output being the panorama. So here with the input photograph for the outdoor case, and that's going to be the input, and the output is this augmented inverse tone mapped outdoor panorama. And for the indoor case, we've cropped out the photograph at this position, and then we've done the spatial warping to get the correct 360 lighting at that position in which we've cropped. So it's next to that chair there. And so the result for this one, for this basic network is, we've got this input photograph, we've trained the network, we can predict the radiance map, and then composite a teapot with that light source. And we can get okay results with that, and this is what the prior work had done. But we've improved it in a few ways. So first, we've introduced what we call a progressive training scheme, and the concept behind it is called curriculum learning. And in AI, what that means is that you train a network with easy examples, and then you gradually refine that network with more complex examples. So in terms of intuition, it's, you know, you learn off by doing simple arithmetic, and you introduce harder concepts until you get to very difficult challenges, and you do it in that order. You do it in that order to, as a human, you do it in this order, but we can also do that for neural networks, where we can train it from easy to hard as well. And so we use this concept for lighting, where the hypothesis was that it's easier to learn rough illumination first. So on the right here, this is called these are different roughnesses of material. So we've got like a low roughness, means like a mirror, and when you go higher, you get this specular, and then you get a diffuse ball sphere here at the end. And so the idea is that we're going to train a network first to learn about the diffuse sphere, and then introduce these glossy spheres and gradually work towards the mirror sphere, where it's got lots of detail to learn. So that's the concept. And so now we're learning these panoramas, when they convolve like this, they're called reflection maps. So instead of learning radiance maps, we're learning reflection maps. This part will have audio. So hopefully you have audio and have a listen. So it's the same as last time, except we're extracting not just in one panorama, but we're also extracting the convolved. We're converting that into the convolved panoramas as well.
We can't hear any audio, right, Andrew?
You can't hear it?
Nope.
Okay, that's fine. I'll just talk about it then. So it's the same idea. We're extracting multiple photos as well in different directions, but the new concept being that we're introducing these convolved panoramas. So we're just taking that panorama and convolving it into different levels. This one does not have audio, so I'll speak over it. And so the progressive training now is, given the photograph, we're going to plug it into the network and train it, and it will be trying to predict the diffuse panorama first and compare it with the ground truth, and then try to minimize that error until it's able to predict a diffuse panorama. And then we're going to transfer the weights of that network onto another network, in which that network will try to predict a lower roughness panorama. So it's going to try to predict something with that looks closer to the mirror, until eventually that will converge, and we keep transferring, and we do this in 10 different levels, from 1 down to 0.1 roughness, until it then tries to learn about the mirror, the perfectly specular case. And so at runtime, the idea is that we have these trained CNNs, and we call this a stacked CNN now, and we predict these different reflection maps. And one of the advantages of this is that not only have we improved the accuracy through this progressive scheme, but we can actually use these trained models independently as well, in isolation, where if we want to diffuse bunny, for example, we can use that network directly, rather than trying to predict with the mirror network and then convolving back down. We can just directly go through that one, which has two advantages. One, it can be faster. You don't have to do a mathematical convolution. And the other advantage is that that network was specifically trained to be diffuse, and so it does a better job at predicting diffuse than trying to go through another network. We did an evaluation of this, where users, so we did a comparison where you would predict using the low roughness network and then mathematically convolve down, versus using each network for that target roughness. And so users would basically have, on the left would be using that low roughness network, convolve down, on the right would be using the one that was targeted for every roughness, so it should be more accurate. And it was randomized left and right, and then they would go through and have a feel at the roughness, and then compare it with the ground truth teapot on the right, and then see how, if they could match the roughness, how well the color looked, was the direction of the light correct, how smooth did it feel? So did it, because since we're predicting each roughness independently, is it going to feel unnatural when you interpolate between them? So we also measured that. So here are some results where the top row is the ground truth for different roughnesses, and the middle is our prediction, and the bottom was the prior work. Prior work did not predict any detail. It was just predicting a model of a light. And so that way we could actually introduce some more detail, and it looked more natural. Another example. To talk through it, our light direction tends to be a lot closer to the ground truth, as well as sometimes the model could be overblown. For example, in this case, we're actually in shadow, not in the direct sunlight, whereas the model had predicted a sun, so it was too bright. It's just our one was able to predict that sort of window a lot better than the prior work. The prior work kind of missed that window and only got the lighting out to the left. Just another indoor case. The prior work was okay. Just ours is a lot closer to the ground truth. The diffuse, again, since we predicted the diffuse directly, is a lot closer than what they had predicted in mathematical control down. It was a bit too bright here. Same thing, our results are just a lot closer to the ground truth. In terms of tone as well, ours is close, more blue, and this is a bit desaturated. So I don't have a live demo with me, right? I mean, it's on the Play Store, and we can add you to it if you want to play with it. But it's a demo in which you can move furniture or cars around, or play with the dragon. I think, and different examples of using AR where we're using this light prediction to improve the quality of putting the virtual objects in the scene. So we're getting towards the end of the talk, but I would like to touch upon some other areas that we're looking at as well. So we'll focus mainly on lighting, but we also have research in material and geometry, which is these other elements of the inverse rendering problem, where we can try to estimate information about the geometry of the scene as well as the material of the scene. Typically for material, they can be quite expensive to capture. You need sort of BRDF capturing devices to measure the reflectance of an object, which is not really practical, especially for like AR or something. As well as geometry, it's getting better at, AI methods are getting better at estimating this sort of thing, rather than using, and LiDAR scanners, I think the newest iPad will have a LiDAR scanner on it as well, but it won't capture, as well as LiDAR, like a full, I think the one on the iPad is just in one direction rather than capturing all around you. So if we're able to reconstruct the material, so the motivation for this is being able to, one of the examples is to blend a virtual object into that, into the real world, such that it reflects into the real world as well. So we can see this virtual sphere reflects in the real sort of window or mirror there. And so it's just a more convincing result that the virtual object is alive in that world. We could also digitally preserve objects, so we could measure objects that are of importance and digitally preserve that object. So we could also do 3D printing with the correct materials and things like that. And so this is one of the research directions that we're going in. I won't go into details here, but it's an active direction that we're going in at CMIC. For the geometry, we did some work on looking at depth fidelity for mixed reality rendering. this was looking at how good did the depth map need to be when you're compositing a virtual object into the scene. So we had this background photograph here. Imagine that's a background photograph in grayscale. And then the depth, you've got the depth representation of the scene. And, it's a bit coarse. And then we're going to inject a virtual object into this, what we call the real scene. So that means the virtual object, when it casts a shadow, it's going to have potentially some artifacts that aren't perfectly aligned with what the actual depth is of the scene. And so we're measuring how accurate that depth map needed to be, like what resolution does it need to be in order to minimize those artifacts. So here's an example where if you have a high resolution depth map, it looks really nice. It casts a shadow onto the bed nicely. If you go too low, you get these sort of artifacts where we're basically taking a depth map and then extruding it into geometry. And so you can see these artifacts appearing here. And then we found an optimal depth map resolution, in this case here, where users weren't able to perceive any artifact. And so here's an example where we've got that photograph. We composited some objects with a high resolution depth map, and then with the lower resolution, which was still suitable. So you can see the artifact path between them, but if you just gave that to someone, it's hard for them to tell that there's an artifact with the shadow going along that on the scene. So to conclude, the focus of this talk was on lighting, but we also look at other areas to do with depth and geometry and material, in which we're actively researching, and we're continuing to do the research in lighting as well. The main takeaways were looking at these technical solutions to innovate the digital media platform using big data and machine learning to solve these problems, and looking at inverse rendering to achieve high fidelity mixed reality rendering. That's all from me. Feel free to do the clap emote reaction. You can do the reaction if you wanted to.
Clapping and some clapping.
TJ's done the clap.
Very good, very good. Thank you very much, Andrew. So